Hi everyone, welcome to my YouTube channel. Today we will be discussing about discrete orthonormal basis. So what is a basis? A basis is a set of vectors which can represent any function in that space as a linear combination, like in R3 space or in 3D space or in real space. We define a velocity, we define a momentum, a position in terms of I cap, j cap, k cap. So I, j, k are bases in 3D space. Similarly, in wave function space, we can choose some wave functions u1, u2, u3, ui and so on to represent any wave function in that space as a linear combination of them. So those constitute a basis and we can choose them so that they are orthonormal. What do you mean by orthonormal? In the previous class we had discussed that if the scalar product or the dot product of two wave functions is 0, then they are orthogonal to each other. And we also discussed that the square root of the scalar product of a wave function with itself is known as norm. So these ui are the wave functions such that they are orthogonal to each other and their norm is 1. So the set ui constitute a basis if every psi which is a wave function which belongs to the wave function space can be expanded in one and only one way in terms of ui's. So you can write psi equals to summation ci ui. So we can relate this with the 3D space. Let's say we have a point xyz whose position coordinates are 2, 3 and 5. So this position vector can be written as 2 I cap plus 3 j cap plus 5 k cap as a linear combination of I, j and k. But there is no other way to represent it in terms of I, j, k. This is the only way. Similarly, if we can represent psi in one and only one way in terms of ui's, then ui's form a discrete set of orthonormal bases. And in 3D space or R3 space, we have defined our position vector as r equals to 2 I cap plus 3 j cap plus 5 k cap. So the coefficient of the basis I cap is I cap dot r equals to 2. So just take the dot product with the basis and you will get the coefficient. Similarly, we are taking the dot product of the basis with the wave function to get the corresponding coefficient. So the dot product of uj with psi is uj comma we are writing psi as summation of ci ui. So we can take the summation outside and we get dot product of uj and ci ui, and we know ci is a constant. We can take it out of the dot product. We are left with dot product of uj with ui, and we have already told that ui's are orthonormal. So their dot product is 1 if both are same and 0 otherwise. So they represents Kronecker delta ij. And if we run the summation over I, so all the term vanishes except when I equals to j. In that case we get cj into delta jj, and we know that delta jj is 1, so we are left with cj. So in this way we can determine any coefficient. Let's say Ci is any coefficient which can be determined as the scalar product or the dot product of ui with psi, where I can be any value 1, 2, 3. It depends on what is the dimension of the basis. Let's say phi and psi are two wave functions which belongs to wave function space F. So we can write those wave functions in terms of basis as summation of bi ui and summation of cj uj. We are changing the dummy index to avoid misunderstanding. So the scalar product of phi with psi is summation over ij. We are taking the summations outside the scalar product and we are left with bi ui comma ci uj, and we know that bi and cj are constant, so they can also be taken out of the integration. We know that the scalar product is the integration, so bi star cj is taken out, and again we get delta ij, which is the Kronecker delta. And if we run the summation over j index, so all the value vanishes except when j equals to I, and at that point we get summation of I bi star ci. Similarly, if we take the scalar product of psi with itself, we get summation over I ci star ci, and we know that ci star ci is mod ci square. From the above discussion, we have seen that wave function psi can be represented as summation over I ui, where ui are discrete orthonormal bases, and we know that ci is a coefficient of expansion, and that can be determined with the help of a scalar product or dot product of ui with psi. We are changing the index from r to r prime to avoid any confusion. So the scalar product is given by ui star psi d3r prime. So we rearrange this term and write it as integration psi r prime into summation ui star r prime ui r into d3 r prime, and this is equals to psi r. So this is only possible if this summation term is Dirac delta function whose peak is present at the position r. So the summation can be written as delta r minus r prime. This relation is known as closure relation, and if an orthonormal set like ui satisfies the closure relation, this relation, then it constitutes a basis. Thank you for seeing my video. If you found any value, please like, subscribe and share. See you in the next lecture.